So we're going to look at this section here of chapter 4. So if you remember, I have said many times, there's two functions in machine learning, right? The inference function, which is that y equal wx plus b, and just making that deeper with deeper architectures. And there's always some objective that we're trying to solve, right? We're the loss function, right? So those are the two main functions in neural networks. When we're doing regression problems, that's kind of how I motivated this problem initially. I said you have the real y and the predicted y, right? And then we would take the difference and square them, and we call that mean squared error. You guys remember that intuition, right? And that's the loss function that we use for regression, mean squared error. Okay. Now, but what happens? So that works for regression problems. But what about classification problems? So we've looked at any kind of classification problem. For instance, Scifar 10, right? So in Scifar 10, we have 10 classes. We have images of whatever they are, and given those images, we're trying to decide what class goes with those images. So that's a classification problem. So for even ChatGPT is trying to do a type of a classification, and it also used the same law, right? That loss is called cross entropy, right? So we've used it already. Whenever we instantiated things, we use cross entropy. So if I go to the GitHub and I go to here, I'm going to go to chapter 4. With this classification of the wine data or iris data set, whatever they are, when we call the core functions after the architectures here, if you notice, we always gave the model a loss function called nn dot cross entropy loss. Do you remember that? So that's what we're talking about today. That one line of code, is what we're talking about today. Okay, and the background of it. It's really important. As I said, lecture, I love to ask questions about this. So, a good amount of questions will be about this on the exam. So yeah, so that's what we're talking about. The loss fn is passed to training, and in the training function, it's used here, loss fn. You see that? So keep in mind, what is happening here is you give, let's talk about Scifar 10, right? So you give XB, and this context would be a batch of images. We pass it to the model, and the model is going to give us all the predicted labels for those images. So that's going to be YPred. And then what do you have here in YB then? If we have in YPred, we have the predicted labels, right, that we're passing to loss fn, then what do we have here? We have the real label. And we need to compare, right, the difference. Do you guys see that? But it's not in the regression problem. It was similar. We would have the temperature, 32, right? And the real temperature, 34. Then another temperature, 89. The real temperature, 7, right? And then you measure the error between those, take the difference, square it. That's MSE. But here, notice, it's different, right? It's a classification problem. So the predicted class for one image might be 7, and the real class was 3. So how do you take a difference between that? You see there's a slight difference going on there. And so instead of using MSE for this type of problem, we use cross entropy. And it's almost like amazing. It seems so complex, and yet when you break it down, it's pretty straightforward. Okay? Everyone with me? So let's get started then. So this was to motivate this idea. I have prepared a Jupyter notebook for this one. So we're going to go over our Jupyter notebook, and we're going to try to understand the background, and I'm pretty sure it'll be clear. All right. So I showed you where cross entropy is, right? So now we're gonna, like, from scratch, try to implement this to get a feel for how it works, and then that's it. So I'm gonna I'm gonna be using these scripts. You can get them from the repo, and the code is available. I'm gonna start the Anaconda environment. All right. dir. I'm going to cd into the desktop. cls. dir. Okay. And I'm going to cd into ITS 365 2025 spring. cls. dir. All right. Then my PyTorch probably. PyTorch. dir. cls. dir. All right. So here I'm going to create my Jupyter notebook. I'm going to start the environment. And activate. And I use that Pi37 2025 ITS 360. All right. Okay, and we can start a Jupyter notebook. Give it a minute. All right, here we go. Okay. I'm just going to create a new Jupyter notebook. I'm going to call this one in class, since you guys like having these. So this is going to be in class cross entropy. Okay. All right. And so that's our Jupyter notebook. Now I'll be using this one. So I'm going to click on entropy and cross entropy. You can get it from there. And this is kind of my lecture for today, my notes on this idea. All right. But it should be pretty interesting. We're going to start at flipping a coin, right? So you guys have probably in your stats course, you looked at that where you flick a coin. You have a coin and you flip it and you know it's heads or tails, and that's probabilities. So we're going to look at that. Okay. So we're going to talk about a concept called entropy. It's a very important concept in networking, actually. I'm sure you guys have discussed it before. It comes, at the whole digital age, right? The bit, using binary instead of analog, all that comes from something called information theory that was invented by a gentleman named Claude Shannon. And he also proposed this idea of entropy, right? And it's a very interesting concept using, the likelihood probabilities to describe uncertainty, essentially. How uncertain we are about something. You know what I mean? So, like, I know for sure tomorrow's Thursday, so there's no uncertainty about that. I have zero uncertainty that tomorrow's Thursday. Do you see that? Now, am I having soup tomorrow? Okay. I don't know, maybe. So then I have, less certainty, right? So that's essentially the concept that we're studying. Got it, guys? So when you're talking about these things, because the way that you phrase something can confuse you, so it's best to kind of go by written things, okay, that you can kind of use as anchors. So I will start with the concept of entropy, and then we're going to look at how entropy becomes cross entropy. And then we're going to see that there's two types of cross entropy, binary cross entropy, and for binary classification, when you have a two-class problem, right? Malware, not malware. That's a binary cross entropy problem. But Cypher 10 has 10 classes, so it is going to be a multi-class cross entropy, and they're different, but pretty clear and intuitive. All right, so let's take a look at where this comes from. All right, so let's describe this. So entropy, so cross entropy is the topic, but entropy is the original concept proposed by Claude Shannon. It is a mathematical idea describing uncertainty. Okay, so you have essentially a formula for it, which is this, where P indicates the probability of something, and this is the natural logarithm or the L2 logarithm of scale 2 of something. So we'll take a look at that. So entropy is a mathematical idea describing uncertainty. So we're going to look at flipping a coin first. So given a very biased coin with both sides having a head, so that's a coin that has head on the same head on both sides, then the probability of getting a head is what? 100%, right? That's very clear. So similarly, the chance of getting a tail for this coin is 0, right? Because you're not going to get that. So in both cases, so that probability itself doesn't matter. What we're trying to measure is the uncertainty of the outcome, right? So similarly, in both cases, we are 100% certain of the outcome. It's going to be heads. Got it? So that's essentially what this problem is about. The uncertainty is 0, and therefore we can say that entropy is 0. So essentially, entropy is looking at this idea of uncertainty, and that's what we're trying to measure. And you would be surprised how much of the digital world depends on that, including ChatGPT, which uses cross entropy as its loss function. So this one concept proposed in the 40s and 50s by Claude Shannon is essential for a lot of deep learning and machine learning. And hopefully what I want you to understand is that they proposed this idea, but we use this idea to train our models for classification. So the uncertainty is 0, and therefore we can say that entropy is 0. So given a fair coin, right? So I'm here now. Given a fair coin with head on one side and tail on the other side, we have reached the maximum uncertainty about the outcome, right? Because sometimes it'll be heads, sometimes it'll be tails. That's the maximum. We have no certainty of it, right? We just have a probability. So given a fair coin with head on one side and tail on the other side, we have reached the maximum uncertainty about the outcome. And here, the entropy is highest, right? So this is going to have the highest entropy. That's key. So the entropy formula then is given by this. So we have entropy equal, remember this is just a sum. So we're going to have a sum of probabilities. So if we have two probabilities, it's going to be, let's say we have two probabilities, P1 and P2. So then it would be P1 times ln P1 plus P2 times ln P2. Do you see that? And if we had multi-class, then it would be the same. We just keep adding the probabilities. This is the formula to measure entropy, which is measuring uncertainty. So the sum is overall potential outcomes, okay? The P, as I've stated, is the probability of those outcomes. So you obviously need that data, but usually you have that data from your data set. All right, so now what I'm going to do is I'm going to plot a chart of the probabilities, and we're going to describe. This is important, actually, because later on, you remember how in MSE, I drew the bowl, right? The bowl shape from MSE, and I explained how that bowl would capture a relationship between the cost and the W's, right? You change the weights and you minimize the error. I'm going to do the exact same thing But instead of a bowl, which is given by MSE, now I'm going to have a different shape, which comes from the cross entropy function. Essentially, this equation now is kind of the equation that we're using, and that will have obviously a different shape than something that is x squared. Do you guys see that? So that's where I'm doing. So, but let's start drawing some shapes and getting a feel for how that works. So I'm going to copy this to my in-class problem, Jupyter. All right. So matplotlib, numpy, hit enter there. Let's give it a minute. All right. It ran perfectly, so no problem. All right. So now I'm going to go over here. And I'm going to grab the next part. This function we're going to discuss, but this function is essentially trying to capture this, okay? So that's essentially what I'm doing here. This equation that I wrote I love doing this. So like I honestly sometimes have a hard time understanding the math equation, but once I see it in Python, it's totally different. So that's what I'm doing here. I'm going to write this one, but as a Python function. So let's go here. This is also, I should state, for the binary case only, right? I'm only doing the binary case. So let's analyze this function. So I've defined an entropy function, and I'm going to plot. So given, I'm going to have an x and y. So I'm going to have a range of x values, right? And I'm going to have a range of x values. And then for every x value, I'm going to plot the corresponding y value. And we can look at it essentially. Because this is a probability, right? In the x-axis, I'm going to have probabilities. So the probabilities will only go from 0 to 1. Any other values are not, are not being used here. So that's why there's these two if statements. So if probability is less than 0 or probability is greater than 1, then just return a 0. That's like outside of the boundaries, and we are only concerned with what's inside of the boundaries. So in that case, that's where so if the value is between 0 and 1, then we're going to execute this line of code here. If you look at this line of code, you should convince yourself that it looks exactly like this one, right? If you notice, there's the negative value, so don't lose sight of that. Negative. This is a sum, so it's going to be of the given probabilities. Because this is a binary probability, there's only going to be 2, okay? So if I, for instance, if I flip a coin, right, and heads is probability of 0.3, then tails is probability of 0.70 in a bias coin. See that? Or if, that's essentially how that works, right? The difference, right? So how likely am I to, do something? Okay, I'm 0.60 of doing it and 0.40 of not doing it. So this formula here, this equation, we can see written down here. Okay, so this is the live code. So it's going to be P times ln P. Just notice that instead of using the natural logarithm, I'm using this log 2, which works better for my case because it's binary. Okay, but essentially that's it. And notice, so I do P and then plus, but because there's a negative, that becomes negative. And then notice I just do the same thing. So if I did P here, then 1 minus P is the other one, right? And so it's 1 minus P times natural logarithm of 1 minus P. Do you guys see that this Python expression is the same as this equation? Okay, they're the same. All right. So now I have that written down in my function. So now the next thing I'm going to do is I'm going to plot this data, right? So using that function, the equation essentially. So what do? I'm going to, first of all, I need to run this one. Okay. Now, all I'm going to do is I'm going to create a plot of values on the X and the Y axis. So on the X, I'm going to call those values XS, and it's just a range from -2 to 2 in increments of 0.1, step size of 0.1, but only care about the values between 0 and 1. All right. And the YS equivalent is just going to be for I in XS, and then we plug in that I into our function entropy Fn. Remember, these are essentially probabilities. So the probabilities between 0 and 1 will go here, and we will just calculate the corresponding entropy. That's it. And then after that, I have my X and my Y, and I just plot it. Everything else here is just using matplot and labeling things. So let's go ahead and do that. All right, and here we are. So that's what the entropy function looks like. Not the loss function, because we're not there yet, but the entropy function. And what's important about this is the probability of head, all the different probabilities. And this is essentially that, remember that function measures entropy. So what is this telling you? If the probability of head is 0, then you have 0 entropy. Do you guys see that? There's no uncertainty. It's a biased coin. If the probability of head is 1, what does that tell you? You know for a fact it's going to be head. So again, the entropy is 0. You see that? But then in between, the value, the entropy goes up or down, and the maximum entropy is 1, and is going to be when the probability of head is 0.5, which makes sense, right? Because that's a fair coin. You know, one side is head, one side is tail, right? So it's a probability of 0.50, but what's important is that it tells you the entropy of it. How certain or uncertain you are given the probabilities of your problem. Yeah, go ahead.
Completely uncertain.
If the probability of head is 1.0, then you have 0 entropy. And the uncertainty is 0. You're sure, in fact, that it's going to be a head.
So at 0.5, you're completely unsure.
That's the maximum unsureness, yes.
Yeah.
You get that?
Yeah.
That's what we're measuring with entropy. It's how uncertain I am. Because sometimes you can, you're not always going to have probabilities like this. The probabilities will vary, but by looking at those probabilities, you can get some confidence about your, what's going to happen. That's really what you're trying to figure out is, how, I cannot predict anything, or I can predict maybe a little bit, and that's always better, right? That I have at least some sense of what's going to happen versus total uncertainty. Yeah, that's what you're measuring. Got it, guys? And okay, great. So this, as I said, this was proposed by Claude Shannon. The entire digital revolution came from these ideas, these metrics of how to measure. Claude Shannon was measuring how much noise there was going to be in the channel, right? So you probably saw this in your networking classes, and you wanted to establish if you had a good encoding scheme or a bad one as you were sending information across the phone lines through the repeaters and all that stuff, and data would get lost, right? So that's what you were trying to measure, given the probability of things. All right, so essentially this is the concept of entropy, so that Claude Shannon proposed. All right, and as it turns out, we used this same idea to create the cross entropy that has allowed us to train our classifiers, ChatGPT, and all that. So now let's go back to, so we've done this part, and let's read through these. And I think some of you asked these questions already. So the top has the least certainty, right? The top here referring to this peak, right? That has the least certainty. At y equals 0, right? You have the most certainty because the entropy, y is this axis, of course, and entropy is 0. You know exactly what's going to happen, right? Where both sides are head and p head equal 1, then uncertainty is 0. When both sides of the coin are tail and p tail is 1, then uncertainty is 0. We know that. The entropy is highest when the coin is fair and the probability of head is 0.5. That's the highest it can be, and the most uncertainty we have about something. So let's do a couple of examples, and these we can just do like here, the computation. I did these with a calculator, so you can do that. I'll make one note about these, which I only wrote on the second example. When I ran these in Python, I didn't use the natural logarithm, but the calculations are based on NP log 2. Right. So you need to just be aware of that, okay, guys? That these computations, if you try to replicate them, you have to use NP log 2 on your calculator or on Python. All right. So we have, for instance, example one, calculate the entropy for coin with both sides as head, right? So both sides are head. So the probability of head is 1. Right? So here we have probability of head is 1. Therefore, the probability of tail is 0. This is a binary problem. So it's the sum. So how do we do that? It's going to be 1 times logarithm of 1, right? Minus the other probability, which is 1 minus 1, or 0. Logarithm of 0. 0 times anything is 0. So that's canceled. And then 1 times ln1 should be 0. Got it? Guys, so that's the actual computation. All right. Example 2 is, so entropy, and to conclude, entropy, you should be convinced that entropy is 0. Why? Because probability of head is 1, probability of tail is 0. You're 100, there's no uncertainty here, right? You know what's going to happen. In example 2, case 2, we now look at a different scenario. Entropy of a fair coin, so that P head is 0.5 and P tail is 0.5. So it's a fair coin. So this has the highest entropy and the maximum uncertainty. We're going to corroborate that. And just as a note, I use NP log 2 from NumPy instead of natural logarithm for actual computation. It doesn't matter as long as you're consistent, right? They both provide the same, not the same value, but provide you with the information that you need. All right, so now I have the formula for entropy, and you can see entropy is equal to 0.5 times logarithm of 0.5 plus the negative of the other probability, 0.5 logarithm of 0.5. You see that? When you do this computation, it actually comes out to an entropy of 1. And that then tells you, if you look at both of these cases, this one has more uncertainty than this one. And that's valuable information for you to make decisions. Got it? All right, so that's entropy, right? And we can actually do a little scenario here. So I'm going to go to the Jupyter Notebook. I'm going to use my entropy Fn, which I already, the function. I'm going to give it a probability, for example, to a 0.5, as you can see there. And I'm going to calculate it. And you can see that it gives me 1. This is really important because remember that this value, 0 or 1 or what, anything in between, is going to be the value that we're going to try to minimize. So remember, what do? You have a neural network, you have a set of weights, and you do all the computations, and you get an entropy of 1 or cross entropy of 1. Then what do you do next? Change the weights again, right? And now you get an entropy of 0.8. Okay, it went down. That's your objective, to have it go down. How do you know now the other question is, how do you know how to update the weights? Do you add the learning rate to them or do you subtract the learning rate? That's where, again, calculus comes in. So the same thing we did for MSC with the bowl shape, we do here, calculating the gradients, but it's just going to be a different shape because it's based on a different function called a cross entropy. Do you see that? It's the exact same mechanisms, just a different function. Any questions so far? Pretty amazing, right? Pretty awesome. All right, so now, anyway, so this is Claude Shannon should have won a Nobel Prize in this. All right, so now that this is done, we are going to look at cross entropy. Not just entropy, but the cross entropy. Same formula, they just adapted it a little bit. So cross entropy can be considered a measure of uncertainty of outcomes due to a mismatch between an actual likelihood of outcomes and what we think this likelihood is. So that's the same as saying between the predicted labels and the real labels, which are also probability distributions. So consider, if we think a coin is fair, but it is not, then we will be surprised by the outcome. You see that surprise is really important. It's a really, as it turns out, is a really important concept in intelligence. You know, why do you guys like comedy? Let's say, you know, we all like comedy, but why do we laugh at jokes? You know, somebody tells a joke and they just say something, but they say it in a strange way, right? You've seen comedians that do this, like, hey, that's an interesting way of putting it. So I'll give you an example. Somebody asked ChatGPT to say something novel about humans. Describe humans, but give us something really novel or interesting about them. And ChatGPT said, okay, one of the things it said is that humans were self-domesticated apes. You laughed. The others didn't laugh, but you laughed. So why did you laugh? Because self-domesticated apes sounded novel to you. You've never heard that before, that description. You know what domesticated is. You know what self-domesticated is. Humans are apes, and you probably agreed with that, but you had never seen that description, self-domesticated apes, right? And it made you smile or you laugh a little. So that's surprise. That's actually tied to entropy because you just had seen the probability of domesticated, self-domesticated, and apes separately, but never together. And that seems strange to you, and that resulted in surprise, which translates sometimes into laughter and comedy. So that's kind of going back to this idea of cross entropy, right? So let's think about this now. If we think a coin is fair, but it is not, right? We had an expectation and it didn't turn out that way. So then we will be surprised by the outcome, right? And that is actually captured by cross entropy. It measures that. So there will be uncertainty about that outcome. On the other hand, if you think the coin is fair, and it is indeed fair, then you will not be surprised. As such, it will have low cross entropy. Do you guys see that? So that's essentially what this is saying. So we think of cross entropy as a comparison between two probability distributions, right? Which is going to be, in our case, the real labels and the predicted labels. So the model will predict that this is a cat or a dog, but it turns out that this was, in fact, an airplane for Sci-Fi 10. That's essentially what this is saying. So we're surprised, and we can use that to measure and train the model based on it. So we think of cross entropy as a comparison between two probability distributions, okay? And that's really important in why we use softmax in the models, right? If you remember, the last activation function that I always gave to you guys is the softmax, which makes all the probabilities add up to 1, making them a probability distribution. So we think of cross entropy as a comparison between two probability distributions. The more they match, the lower the cross entropy. And by the way, that's our objective, right? To minimize a value. And so this is why we use cross entropy. An exact match is equal to 0 cross entropy. So what does that mean? It means that it predicted that an image was a cat, and in fact, it is a cat. Then it predicted that something was an airplane, and it is in fact an airplane, right? So that's when you have that, you will have 0 cross entropy. And then therefore, if you make that goal for your model, the weights will be adjusted towards that, and you get a good classifier. In NNs, the pred outputs for classification are a probability distribution, and the real outputs are also a probability distribution, which you guys should understand. Got it? So here we have, for cross entropy, we have the exact same formula as before. The only difference is now we don't use the same probability. Instead, they are the same probability because it's the probability of a cat, right? But now the difference is one is the predicted probability and one is the real probability. Okay? So we'll see that in a second, but essentially now cross entropy is going to be the sum over all the probabilities, but it's going to be the y real times the logarithm of the y pred. Still of cat. This is still probability of cat, but this is a real and this is a predict. And we do this sum for all the classes, and that gives us a value of cross entropy. And all we have to do is minimize that, and boom, we train any classifier, including Cypher 10, ChatGPT, and so on. Any questions? All right, great. So here's a couple of examples. So once again, I have some examples. So let's take a look at this one. So this example, YPRED. So the model, our neural network, predicts that for that class, cat, it is 0.9. But the real class is 1, right? So that's how it is. So then we can measure the cross entropy. So it's going to be class 1, right? This is for the binary problem, by the way. So this is for the binary. So this is going to be 1, right? Which is the real class here, 1. And then the predicted is 0.9. So 1 times logarithm of 0.9. For the other case, 1 minus 1 is 0, so this cancels out for the binary problem. So if we just do this calculation, that gives us a cross entropy of 0.10 or 0.105, right? All right, now let's look at the exact opposite case. So the class is still 1, cat, right? But the model says it's a cat with 0.1 probability, a much lower probability, right? It's 10 versus 90, 10% versus 90. So you do the computation, it's going to be 1, the real class, times logarithm of 0.1. This is 1 minus 1 is 0, so this cancels out. Notice that the cross entropy comes out to be 2.303 versus 0.10. Do you see that? So the loss function here is going to, cross entropy goes down as the model gets better. So that's, it's trying to predict if this is a cat, right? The label is 1, and it said it believes it's 0.90, right? From 0 to 1. So that means it's pretty certain that it's a cat. This is almost like saying the following. If I read Y real, I say I have 100% probability or confidence that it is a cat. The model is saying I have 0.9 probability or certainty that it is a cat. Do you see that? So what could you conclude about both the model and the real? They're both pretty certain that that's a cat. You see that? That's what this translates to. But if I look at this other scenario, the real model, the real says, okay, I have 100% probability or certainty that it is a cat. But the model is saying, I have only 10% probability or certainty that it is a cat. So the model is not very sure of the prediction, and therefore the prediction is actually bad. So what you want to do is, and this is reflected in the cross entropy. This has a higher cross entropy because the model is more uncertain about what it's doing, and it's not a good set of weights. So you want to keep adjusting those weights until the model has more certainty, and you measure that in one metric by reducing cross entropy. This is a key concept here. Any questions on this? And that's it. If you understand that, then essentially that's how we train all these models to become really good classifiers. These are for binary, but I'm going to do one more example for multi-class in a second, just to drive the point. Now, one thing that happens is, if you notice, when I was doing the binary case, we would look at one probability that was one. We were saying this is a binary case. So then the other probability becomes 0, right? Which essentially cancels out the term, right? So it just depends on which one you're looking at. If you're looking at this one, think of it this way. If you're looking at this one, then the graph has a shape for that loss. And if you're looking at this one, then it has another shape for that loss because they have like slightly different objectives. But now I'm going to try to relate this to the bowl shape, right? If you remember, because we're still looking at that, we just have to understand that when we had y minus y hat squared, we had a graph that was a bowl shape for the comparison between weights and the losses. Now we have a different formula, obviously it's natural logarithms, so they don't create a bowl. They create these curves, right? And we're going to look at it. So we're going to have actually, essentially we can say we get two graphs. So if in both of these examples, this one and this one, the y real was always 1. So we were always looking, this was always 0. This part here was always 0, and this part was always here. So we were just looking at this part, and this had a graphical representation. And given that graphical representation, when we do stochastic gradient descent, we descend on that graph. If we, on the other hand, had gotten the other label, 0, then we would have been, this would cancel out, and we would have been on this side. So then that graph looks, different because it's a different function. So that's what I'm going to do here. Okay, so I'm going to copy this. And show you the graph. So here, all right, so this is the same function, right? I'm gonna the cross entropy function. Just I worded it a little bit different, right? Then I'm going to generate my data. And if you look, I'm going to say the X range is going to be from -2 to 2 with step size of 0.1. And then I just take all those values and I'm going to run them through my cross entropy function, but for only the cases where the real label is 1. Okay, in this binary problem. And then I'm just going to plot it. And as you can see, imagine this is a curve. It came out a little less curvy, but it's a curve that starts and it's going down like this. Do you guys see that? So essentially, what is the goal here? The real label is 1. Do you guys see that? The real label is 1. We want the entropy to go down, correct? Which is the cost. Remember, that was the goal. Right? And so what we want is, we want to change the W's so that the probability becomes 1. Because the real case is 1. Remember, the real case, so actually it's better here. Which one was the objective here? Which one would you prefer? This case or this case? The first one, because we want to have more certainty. If you notice, this 0.9 is closer to 1 than 0.1. You see that? We're trying to make this, the real and the predicted, be equal to 1 for that scenario. And the way that we do that is, remember that this 0.9, where is that coming from? Where's that 0.9 coming from? The model's prediction, the neural network, exactly. And what's the thing that controls that prediction in the neural network? The weights and the biases. Remember that that's always what we're adjusting. The switches in the perceptron, same thing, just a different goal. So think about it. The model, Cypher 10, you're changing those weights, and what it's outputting is that 0.9. and it wants that 0.9 to be as close to 1 as possible, right? So this is the equation that we use, but remember that these equations have a shape that translates intuitively into this idea of going down the gradient, right, to the lowest point. And so that's what I did with this graph. So I'm showing you the equation, and I'm also plotting it for the case of 1. So now you can see essentially, remember that this is dependent, right? That 0.9 is dependent on the weights. So as you start changing the weights, if you're here, right, and you take you calculate the derivative, what does it tell you? The gradient is that way, right? So keep going that way and adjusting the weights. Do you guys see that? So that's essentially like the bowl shape, but captured for this specific cross entropy function. So now we can do the other one, which is going to be the case for 0. So the case for 0 is this other side. So if I give you a y real of 0, so if this had been 0, then this would be 0, correct? So it cancels out this whole term, and then you have 1 minus 0, which is 1 times log n. So essentially the other side of the equation, one or the other. And so that has a different shape, right? And that's what I'm going to plot. Now, I'm going to do that here. You can see that's the same equation, the same thing, but notice in the cross entropy, this is now 0. Instead of it being like in this example, it was 1 because we were looking at the case when the real label is 1. Now we're looking at the case where the real label is 0. Okay? And when the real label is 0, what is our objective? Our objective is to minimize entropy, correct? We want this value to be as low as possible, correct? And how does it get low? By descending in the gradient towards what? Probability of 0, because the real label is 0. So another way of saying this is when the real label is 0 for the binary case, you want to use this graph. And when the real label is 1, you want to use this graph. Because when we're descending, this takes us to 0. And when I'm descending, this takes me to 1. Now, this is graphically the interpretation so that you can tie this back to stochastic gradient descent for MSE. But essentially, this shows you that the equations are essentially just graphs. And you have one case or the other. And that's it. Like, that's literally it. Any questions? All right, so we've looked at the shapes. So you've seen that there's also this graphical interpretation, right? Just like we did with MSE. Now this was binary. This was the binary case, which is easier to view and visualize. Now I'm going to do the multi-class. So let's just analyze. So we've done this one and we did that one. So we finished this Jupyter notebook, okay? So this one's done. Now I'm going to go back to your notes. So remember, I provided the notes that you're reading. And I go to content. Content. All right. Cross entropy. We're going to click on cross entropy and well, actually, I'm going to go here. OPIC notes, right? This is where yeah. So you guys are reading through this chapter and hopefully you've read all of this already. Linear regression we've covered already. R square we've covered. Linear regression we've covered. We're on logistic regression. Cross entropy here. So this is where we are. So this is the Jupyter notebook I just did. So in the linear regression example, we use the least squares error loss function, or MSE, the bowl shape, right? Y minus y hat squared. In this case, we now use a logistic regression cost function or cross entropy. I should have said a classification function, but it's because here I'm talking about logistic regression. So logistic regression and other classifiers use a cost function called cross entropy. The cross entropy compares the real labels to the predicted label. This is what I just said. All the examples I provided so far are binary cross entropy. So that's because it's the simplest concept to understand, but that essentially was like your malware, not malware, spam, not spam. That's a binary classifier. There are actually two types of cross entropy. They are the binary form of the cross entropy for two classes and the multi-class cross entropy. So I just described the binary in the previous Jupyter notebook. This is just another way of describing it. The graphs are a little bit better, but it's essentially the same thing. When the real label is 1, the formula cancels out to look like this, and you're essentially trying to optimize, right? Minimize this cost, which takes you to a probability of 1 to be the same as this probability. When it's 0, then the one side cancels out. You're left with the other side. Your goal is still to minimize the cost. So essentially, you take the gradient descent until the probability is closer to 0. Okay? So that's the binary, and then this is the formula. Multi-class is actually pretty straightforward too. And that's when you have more than 2 classes, such as Cypher 10, which has 10 classes. Iris has 3 classes, and so on. Okay? So the best way to understand, you can read through this, but the best way to understand this is probably with an example, right? So I'm going to give you an example, and I think this will make it very clear. Formula is the same as before. So let's take a look. An easy way to understand the multi-class cross entropy loss function is with an example. So we're going to assume that we're training a neural network to predict one of 5 classes. So assume we try to classify images of vehicles, right? And we have 5 categories, which are plane, car, boat, bike, and balloon. Okay, these are the 5 classes, discrete classes. They would be, that we would be trying to do. Given a cross entropy model, we have the following output vector for this multi-class problem as such. So this is the model, right? This is the model predicting. Okay, so you built a neural network, it took images as input, and the output was a vector. So you had the input layer, let's say 5 hidden layers, and an output layer. How many neurons do you have in that output layer for this scenario? How many neurons? For this class? Huh? For each class. The features are the inputs. The classes are the outputs. So what's the size of that vector? The output vector, what is it? For this scenario, Q1. 5. Exactly, right? So essentially, just like remember with Setosa, Virginica, and Versicolor, right? You had 3. For the Iris data set, you had 4 inputs, 3 outputs, and however many hidden layers in between. For this problem, you have 5, right? So what is this telling you? So given a cross entropy model, we have the following output vector, right? According to this model, the model is saying, I think as a model that this image is 30% plane, 20% car, 5% boat, 5% bike, 40% balloon. Another better way of saying it is I think that the probability that this image is a plane is 30%. The probability that this is car is 20%. The probability that it is boat, 5%. The probability that it is bike, 5%. The probability that it is balloon is 40%. Several problems with this. One of them, those probabilities do not add up to 1. Ideally, you would want them to add up to 1. Do you see that? That doesn't break our example, but just, as a point. Also, so essentially it's saying the model says, well, I think this is either a plane or a balloon. That's essentially what this is saying. It's not very certain. You guys see that it's not very certain? Okay. The model is not very confident about what type of vehicle it is. In contrast, the label for each image would tell us with great certainty, right? Because the labels are 100% certain. So what is the vector for the labels going to look like? Well, if it's an airplane, it's going to say, I have 100% confidence that this is an airplane. So the probability of this being an airplane is 100%. And the probability of it being a car is 0. The probability of boat is 0. The probability of bike is 0. And the probability of balloon is 0. Do you guys see that? So that's the relationship. So the real labels are a distribution that is very certain, and the predicted values are a probability that is less certain. The goal, though, is for that model to become more certain about what it's saying. So we can calculate the cross entropy given this information to measure our model's cost. So this is what we're trying to minimize, right? So we're going to update the weights based on this information. So for instance here, notice it's the same P times log of Q. It's essentially, P times the logarithm of the probability, the predicted versus the real. So it's the same equation, and we sum it over all the classes. So now we can do the calculation. If we calculate the values for multi-class cross entropy, we get the following. So the real probability, for this scenario, right, Q1 and P1. So the real probability is 1 that is plain. So you can see 1 here, right? The other reals, if you notice, are what? 0, because the model knows that it's an airplane. It's the real data and not the other one. So it's 1, 0, 0, 0, 0. And then here we add log of the predicted value. So we know that the model thinks it's a 0.3. So 1 log 0.3. Not very certain, but that's what we're trying to change, right? And then for the other one, it would be 0.2, 0.05, 0.05, and 0.4, which correspond to the values in this vector. So that's how you calculate the multi-class cross entropy. So if you do this computation, it'll give you a cross entropy of 1.2. Do you see that? So that is the value that we're trying to minimize in this problem. So that was, let's say, at the beginning of training, the weights were not really great. It predicted this vector, compared it to the real, and it gave us a 1.2 cross entropy. After training, it's training over time, and it adjusts the weights every time based on this metric. After training and after it has a really good set of weights, then we recompute. So now it says, after training, the model is much better, and it can predict the following. So now notice that the real vector is still the same, 1, 0, 0, 0 for an airplane image. And this is what the model says about that image, right? Now it thinks that it has a probability of 0.98 that it's an airplane. You see that? And it has a probability of 0.01 that it is a car, 0.01 that it's a bike, I think, and so on. Right? Do you see that? So obviously this is a much better model. And this Q1 now, given the label as before, we can use that information to recompute cross entropy. So as you can see below, the cross entropy is now lower and optimized. So it's going to be 1 times log of 0.98, so 0.98 and the 1. And then these are 0, 0, 0, 0, the real values. 0, 0, 0, 0. And then the predicted values are 0.01, 0.01, 0, and 0. When we compute this cross entropy, it is now 0.02. So obviously 1.2 is higher than 0.02, and it just so happens that it corresponds to the model predicting better. Another way of saying this is, as cross entropy goes down, this is going to improve. And the model just becomes better at predicting those probabilities. Remember that what the model predicts is these probabilities. And then to get the label, all you do is you grab the highest value. So here, what would be the label? If this is the highest value, 0.98, then the max label is 0. If 0.98 was, say, at the end, and everything else was zeros, then what would be the label for this one? Max label for this vector will be 4, right? So it's 0, 1, 2, 3, 4. If the last one was 0.98. But that's how it works. So in classification, the vector is predicting a probability distribution over the classes. And you pick the highest one to be your label. And we do all this using cross entropy, essentially. And that's it. That's the whole discussion. We've gone from entropy to binary cross entropy to multi-class cross entropy, and with an example of, for instance, images. All right. There will be about 5 questions related to this on the exam. No, I'm kidding. But yeah, that's it. So that's the topic of cross entropy that I wanted to cover today. So this is one of the not hardest, but maybe the most theoretical topics. Yeah. So great. Please continue to read all the notes and practice all the examples. And yeah, that's it. So we'll stop here for today.